Hello all. So basically this is going to be a really quick one because a lot of these questions are from review week 6. So I'm just going to kind of skip through those and just go on to the ones that are new. So literally the first one I'm going to go through in recitation. But just remember these kinds of ions you do need to memorize. There's things like sulfate. When you have sulfates, those things are things you should do. So sulfate versus sulfites versus carbonate. These are all the kinds of words that I would remember, when you're going through this stuff. Ammonium is one of them. Nitrate's one of them. There's nitrite. That's a good one to remember. Things like these are ones that I would remember for future reference, because even though it seems like you can look them up all the time, in all honesty, when you're in a store even and you're picking up a prescription, it's always so good to be able to say to yourself, oh, I kind of know what that is. Do you know exactly what it does? Probably not, but it's always kind of a nice feeling to know, oh, carbonate is actually that was a horrible C, but it's actually a carbon molecule that's then bonded to 3 oxygens, you know what I mean? And it has, a -1 charge. It's always good to look for things like that, you know what I mean? Like to be able to say that to yourself, that you know what that is, especially because, vitamins have things like nitrites in them all the time. Your shampoo has sulfite and sulfates in it. These are things, that if you know what it is, it's kind of nice to know. That's why sulfates dehydrate your hair, things like that. So again, 2, 3, 4, those were all in last week, so I'm just going to skip through those. The answers are there if you want to write them down. So for number 5, the following questions are about acetic acid and hydrochloric acid. So this should kind of seem familiar from when you guys were doing some stuff on your, CD, whatever stuff that you did in your activities, as well as in your lab. So based on Lab 5, which one would you expect to be stronger? What does it tell you about the percent ionization? So again, we have acetic acid and hydrochloric acid. If you do not know the strong 7 acids by now, then you should really memorize them, because these are things that will come up all the time. That will come up all the time, and if you don't memorize them, then you're going to have issues later. So HCl is one of them. HF is not, so don't think that it's all the ones at the end, things like that. So this is a strong acid, so I'm going to put SA for strong acid. And then acetic acid is a weak acid. So whenever it asks you to talk about the acids, it's talking about, percent ionization. And as we know, strong acids, those are going to be 100% dissociated. They are going to be ions. So when you're talking about a Ka value and you're talking about strong acids, please, please, please remember that you are not going to have HA anymore. That is completely dissociated. Meanwhile, when we talk about weak acids, those are less than 100. So when you think about that, that means that you will have an HA now, because you're now not going to have a full dissociation in that sense. So keep that in mind when you're doing these kinds of things, because it's very important. Next, calculate the pH. So we know already that with acetic acid, this is a weak acid, so I'm going to have to do x squared from my ice table divided by the concentration of my acid, so 0.5, and that's going to equal my Ka value, not my pH, just it's going to get me my x value overall. So that times 10 to the -5. So then what I'm going to do is I'm going to multiply this by each other, and when I multiply them together and I take the square root, I get that x equals the concentration of hydrogen ions. And if it equals the concentration of hydrogen ions, I've just got to plug that into my calculator, which I'm going to do in a second once I type out that x equals the concentration of hydrogen and nothing to do with pH, because I saw that mistake a lot. So when I plug this in, if I can plug this in, I'm basically just going to type into my calculator 1.8 e to the -5 times 0.5, and then I'm going to take second square root of my answer. Where's my answer key? Oh, there it is. And I get this value here, 0.003. Cool. Okay, so that's what my x equals, is 0.003. And remember, then I just have to take the negative log of this number, right? If we take the negative log of that number, so now I just take the negative log of x, aka 0.003. I'm expecting a pretty low overall pH, because when you see a very high concentration, and this is considered pretty high in comparison to this, it's going to be probably more acidic. But let's just check. Catalog log 0.003, and there you have it. I have 2.52. Now, when I now take, say, the negative log of my 0.00010 number, so again, we're going to say 10 to the negative, 1, 2, 3, 4. I'm now going to get a much smaller number, probably 4. We can kind of make that guesstimate. So I'm going to put 1 e to the negative 4, and there you have it. I get 4. So when I do that, now I can see that when I plug all this into my calculator, I am getting the numbers that I thought I would be getting. Now, does our calculation match our prediction? Well, we can say with certainty that no, it doesn't. We thought that our HCl was going to be a lot stronger, but in reality our weak acid was, and that's all to do with the concentration of our hydrogen. The strength of an acid does not predict in any way how strong the acid is going to be in pH. pH does not determine that straightforwardly. It is determining how much hydrogen ions are in solution. That's it. That's all it's doing. That's not to say that something with a pH of 1 is not super acidic. It is, but a weak acid, if concentrated enough, can be just as deadly as a little bit of hydrochloric acid, okay? The only thing that makes hydrochloric acid a strong acid is that you need less of it to get to that pH, right? So this is, 2.52, but that's because it's quite less concentrated. So it's all about the concentration. Okay, so again, 6 we did from week 6, so I'm going to skip it a little, and here we go. We're going to calculate the pH of a buffer. So again, we're using a pretty dilute acetic acid and even more dilute conjugate base. We can always tell it's the conjugate base because we've got a salt in there. So again, I'm just going to plug in some numbers, right? I've got my initial concentration of my acid. That's pretty straightforward. But now we have a concentration of conjugate base, right? We have 0.15. So this is where you have to make the Henderson-Hasselbalch judgment here. And you have to say, okay, who has more, who has less, and how am I going to relate that to each other? So when we always think of equilibrium and where it's going to tip in terms of equilibrium, I always have to think, where's there more? Because wherever there's more, it's always going to tip the scale to where there's less. So in this case, when I look at 0.05 and 0.01, 0.05 is more concentrated than 0.015. So that means it's always going to tip this way. So I'm going to get plus X on this side, and that's going to be for both my conjugate base and for my hydronium ions. And then I know that my acetic acid will be less, so minus X. So then when we drop these down here, we just do 0.05 minus X, etc. So you see I've plugged that in and I've set it equal to the Ka value, as you should, because remember, Ka equals the concentration of our two products divided by the concentration of our reactant. And so then I set that equal to my Ka value, and I get the X equals this really long number here. And so when I have the X equals that super long number, I then could just take the log of that, and I can say, okay, now I have my pH. So when you finally have your pH, now they're going to ask you to take the shortcut. If it ever asks you to get the pH and it gives you the concentration of your acid and the concentration of your conjugate base, you can simply just use the Henderson-Hasselbalch equation. Literally this equation here. So what I'm going to do is take first the negative log of the Ka to get my pKa value, which here I find is 7.74, and I know that my pH equals my pKa value plus the log of 0.015, again conjugate base, divided by my weak acid. So again, the biggest thing here is plugging in numbers, but making sure you know what you're plugging in. So then I basically just take the pKa minus the negative log of that conjugate base divided by the conjugate acid, which turns out to be minus 0.522, which again equals 4.2. Okay, so the same thing with these numbers. So they all equal each other, and that's what we expected. All right, this one again is from last week, so if you need help with that one, let me know. But essentially, if you're using the Henderson-Hasselbalch way, this is the way to do it. So pause your screen and take a look at that. But just know that when it says to make an acetic acid to sodium acetate buffer, be sure that you realize that this is conjugate base to weak acid. So your overall ratio is going to be the opposite, right? Because you're wanting acetic acid to acetate buffer. So you're wanting weak acid over conjugate base, but in the Henderson-Hasselbalch equation, it goes conjugate base to weak acid. So you're going to have to do a flip. Otherwise, you're going to get a really weird number when it really should be 1.8. Okay, so just make sure that you remember in the Henderson-Hasselbalch equation, it's conjugate base over weak acid, but if it asks you to make an acetic acid to sodium acetate buffer, that means it wants acetic acid, aka the weak acid, in the numerator and sodium acetate in the denominator. So this is obviously flipped to what it's asking. Okay, thank you guys so much, and I will see you guys next week.